Hello, all. My name is Jana Iyengar,
And I'm Bharat Raghavan.
and we are here today to talk about how to change internet architecture from a practical perspective. The questions that we want to engage on today, that we will engage on today, are how does internet architecture change today? What are the forces at play? And importantly, what principles can we draw from our experience, our collective experience? Our goal here is to sort of try and articulate how one can be more successful in changing internet architecture in this reality. Um, so our perspective here really comes from both of our collective work on systems, protocols, and architectures in both industry and academia. We worked on both clean slate and also practical architectures over a number of years, and that's where we draw our experience from. Our discussion today focuses on the global artifact that is the internet, and specifically the capital I internet. Though the principles that we outline here should broadly apply to any large multi-stakeholder system. So before starting though, no, well, maybe right at the beginning, I'd like to say we want to just delve a little bit into how the internet as an artifact specifically has changed over the past 40 years. The internet in the 80s and the 90s was much smaller scale in terms of both traffic and in terms of relevance to the world at large. Multiple architectures and artifacts did coexist back in the day. There were many competing network protocols, many vendors, many implementations. Eventually, something won and got deployed. OSI was in the running. TCP became TCP and IP. Various core architectural principles were established, recognized, fought over. The IETF was established, and even forklift changes back in the day were actually possible. We can't even imagine flag days today. This shifted a little bit in the 90s, where the internet started to harden. IP multicast, for example, was developed and deployed widely, I would say, but without a particular goal or driver in sight. IPv6 developed and was somewhat deployed, but then got stuck. DiffServ saw an interesting trajectory. Again, it got somewhat deployed. And then you get to the 2000s, where the 2000s saw industry use the internet at scale, and it drove scale of the network itself. The 2000s also saw a different emergence. It saw an emergence of industry from the internet. This is not just businesses using the internet, but, sorry about that, businesses, not just businesses using the internet, but building it and extending it. Large-scale businesses, internet-based businesses were already there, and they grew dramatically. CDNs, router vendors became bigger. Telecom and cable operators deployed native IP switches and started to switch over to IP as primary. Middle boxes and ossification of plain text protocols was underway with the organic growth and scale of the internet's use. The 2010s saw the growth of what I'll now call internet businesses driving internet growth. There was growth of mobile and mobile clients, which became the majority of internet and user devices. And this was dominated by a small handful of businesses. Streaming on the internet by a handful of businesses became dominant traffic. Cloud services for application servers became a thing and grew dramatically through this decade. Cloud, CDNs, ISPs, mobile apps, and client vendors, dominant application services like streaming, gaming, teleconferencing, all saw tremendous growth. And consequently, architectural control sort of shifted to these entities. This, in our opinion, was the decade of sort of a consolidation of internet architecture through businesses, effectively shifting what we call change control of the architecture itself, of this artifacts architecture, to businesses' economic interests, almost entirely driven by massively increasing scale. So flash forward to today, we have seen significant growth of industry from the internet, not just businesses using it again, but businesses that are building and extending it. This industry emergence, or the businesses building the internet, continues today. Cloud infrastructure, for example, dominates where application servers run. CDNs are almost always used for scaling and dominate where protocol servers run. ISPs are all IP carriers, not just phone companies. ISPs and CDNs are almost entirely directly connected, and the radius of the internet has considerably shrunk since the 90s. Application services, the things that users are interested in, such as streaming content, gaming, information, Gen AI services, and many others, are popping up and growing to become hardened. Now, this hardening is not a bad thing. I just want to be very clear here. This is a narration of a history of success. Hardening of any complex system is a side effect of massive success. The internet has succeeded in not only enabling businesses on it, but global scale businesses that build it. Bharat?
Yeah. And so, one of the things that we see is that there are unusual ways that this manifests, that this sort of economic incentives pop up. And so you might be wondering, why are we showing Fortnite here? It turns out that Fortnite game downloads right now are a significant load on the internet today, and have been for some years now. Every month there's a game release, a swarm of users downloading hundreds of gigabytes at the moment that the release launches. And this crowd creates such a massive load on CDNs, on ISPs, that for a short duration every month, every CDN in the world and ISP around the world is impacted by this game release. And this is not that widely known or observed, at least from what we know, but it's just one example of a pain point across stakeholders in the internet. But these are pain points that have sort of intricately linked economic opportunity and friction across content publishers, CDNs, ISPs, and others. And pain points like this also drive changes across stakeholders. They are actually motivated to make changes because of Fortnite game downloads or other unusual new patterns that are emerging across the internet. And these are opportunities for an architectural rethink in addition to just dealing with the economic pain. And there's several such examples, persistent opportunities for these friction points across stakeholders that we think can drive change in the internet architecture as we go forward.
So we acknowledge that there are many legitimate incentives to driving change. Historically, even internet architecture has seen different motivations that led to changes in it. However, with the dominance of large economic players in the architecture today, economic incentives tend to dominate. We do not get into a discussion here of how to make other incentives viable. They are absolutely worthy, and we know that this is a discussion that is worth having, and we would love to be a part of it when we make that happen. For example, policy has become a strong tool for protecting non-economic incentives, such as with privacy, for example. As another example, whether you agree or disagree with net neutrality and its success, the principles still define network architecture today in practice. Now, we don't go into policy separately also because while it has pretty massive and direct bearing on economic incentive structure of the stakeholders, it is a tool. We argue that the consequent economic incentives still remain the primary driver of change. So any architectural change of the internet today has economic consequences for the stakeholders. Aligning those incentives among stakeholders or creating enough incentive to force that alignment maximizes chances of success in today's internet. Now, we rush to say two things. First, this is an articulation of the status quo, not a defense of it. Second, we do not suggest that academic work should always engage with economic interests, economic incentives, or consider how to make those work. There is tremendous long-term value in clear thinking and articulation of new architectures, even those that are impractical today. But articulating incentives is important, and economic incentives are necessary to consider if you want success in deployment today. So let's look at 3 examples of changes that have happened on the internet in recent times anyway. And it's odd to say IPv6 is recent. However, let's consider it because it's worthy. The economic argument does lie underneath them all, but it's also interesting to see how these pretty wide-reaching changes of diverse technologies have happened. Some are more architectural than others, but they're all significant and persistent changes to the internet artifact. So let's start with IPv6. Now, while IPv6 itself is just, we could just argue it's a protocol, but the address space scarcity in IPv4 definitely drove some fundamental architectural changes, like the adoption of carrier-grade NATs or just NATs in general, the loss of IP addresses as endpoint identifiers, for instance. This is also a great example of a global change requiring massive coordination and incentive alignment across most of the stakeholders of the internet. And so it gives us a lot of interesting lessons that we can learn from this. The ideas for V6 were developed in the 90s, but deployment stalled pretty much soon after with classless routing or CIDR and with NATs. Eventually, we saw deployment as the cost of IPv4 addresses went up. Newer ISPs, like mobile ISPs and ISPs in the economic south, probably saw this cost advantage and built right from the beginning for IPv6. Note that most of the technology and even vendor support has been there for like 20 plus years. Adoption and use, however, requires economic incentives to be strong for local deployment or alignment across stakeholders for global deployment. Let's look at QUIC next. QUIC would traditionally be called an application protocol because it runs on top of UDP, but it isn't. It's a transport protocol. It's a transport and security protocol. It implements traditional transport functions like congestion control, loss recovery, and even end-to-end authentication and confidentiality protection. QUIC is an example of deployment of a new transport protocol that itself got deployed because it ran on top of UDP. One, that was a practical matter to get through middle boxes. But then it drove down latency for application services with economics that are very sensitive to latency, like web page load or video load latency, for example. Notably, there's an important point about QUIC itself was that it was built to enable things in the future, encrypting all of the QUIC protocol headers and application data. So future architecture evolution was possible on top of it. We'll talk about this a bit again soon. QUIC now enables new architectures on top of it. You can see Apple's Private Relay as an example, or Media over QUIC efforts. Both are efforts that leverage being above the encryption or the encrypted layer in QUIC, building overlay protocols and architectures on top of it. Third, WebRTC. WebRTC fundamentally changed how web applications, specifically browsers, handled real-time media and drove the growth of video conferencing, online gaming, and other such applications. WebRTC is, again, what we would have been considered traditionally an application protocol, but it is not just that in practice. It is an entire architecture, including centralized and decentralized instantiations that are possible, with signaling, with turn, ice, and stun servers, with many different possible variations that are all currently used today. The protocols themselves can arguably use refinement. We won't argue that. But the fact that we have managed to build and deploy this at scale, or multiple scales, is testament to its success as an architecture. WebRTC was timely. It owed its success to open standards on a timely problem, and of course, running production code. Technically, WebRTC was built as an overlay over UDP with built-in encryption again. Running on UDP made it possible to work through existing middle boxes, while encryption again limited the ossification of things that it used, the protocols that enabled these architectures. Now, these examples, the three examples we talked about here, are diverse, but we're going to try and pull some common threads. Not all of them always apply.
Yeah, so what we can do is we can consider sort of a past, present, and future. How do we get here? Some of what John had just talked about. Present, consider what are the stakeholders now and what do they care about now? And then the future, how do we protect that architectural change? And so, what we've talked about so far points to a way to think about internet architectural change. And it's important for any change that we make to consider the past of how we got here and what these stakeholders care about. And we want to shore up that architectural change so it doesn't get undermined. And this is perhaps a slightly different way of thinking about architectural change versus a systems first or bottom up technical stance, because our goal is to engage with history, incentives, and stakeholders alongside the technical considerations that we're always going to have. And so we've talked to history and incentives so far. So let's dig a little bit deeper into what we mean by stakeholders before we talk about how to make change happen and how to protect it. And so we refer to stakeholders as those who can exercise change control over the internet. So any multi-stakeholder system, it requires that engagement with all the stakeholders. And this is always true, but we can refine this understanding a little bit.
Oops, sorry, went too far there. So let's first list the stakeholders that we see in the internet architecture today. Now, change can happen within each of these stakeholders or where a given stakeholder has complete change control. But these are the stakeholders that we've identified. There's cloud vendors, there's OS vendors, there's CDNs, ISPs that used to be telcos and others, but everybody is an internet service provider today, content publishers and applications. And I want to note that governments are also an important stakeholder, but again, we don't get into governments and regulation and policy in this talk, but it's definitely interesting to talk about. So change can happen within each of these stakeholders, where when a stakeholder has complete change control within themselves, they can make those changes happen, or changes can happen across these stakeholders where some sort of engagement obviously becomes necessary. It is obviously, again, easier to have changes to be within a single stakeholder's change control than across. But when it's limited to within, it limits the scope of changes that are possible. Once again, governments are important stakeholders, and they're so much more important now than they were 30 years ago. But we do not have enough time to get into that in this talk, so we will let that be for this talk and hopefully get into it in a later one.
So we've got these stakeholders, and they each have their own incentives. And in this, we're going to focus on their economic incentives to make changes in the internet. So one thing we might do is break down how do they achieve these changes? How do we contextualize the efforts of the stakeholders and those of researchers that may want to, make some changes of their own? So for lack of a better framework, let's consider what kinds of outcomes are being sought and what control the stakeholders have in making those changes. So as we've discussed, change control is what can a stakeholder or group of stakeholders unilaterally do, and outcomes are what initially those changes can accomplish. So let's consider CCN, content-centric networking, as an example of a clean slate proposal that really was a new internet architecture that could have replaced IP with a content and object-centric approach, but would have required multi-stakeholder change control, basically global, and if deployed at scale, would have had global outcomes and impacts. IPv6, of course, has been similar. Global change control, of course, is the hardest because of the many stakeholders and their individual incentives, which may be at odds with each other. And we'll come back to Quick in a second because it's an interesting example with a little bit of both. Another quadrant here is local outcomes with local change control. A very common case, much easier, lower global impact, of course. And this has been the quadrant that a lot of research has gravitated towards in the last decade or a little bit longer, because there are large-scale networks being built by companies that have complete control over their environment. And that means that it isn't affecting necessarily the capital I internet, but it is large-scale networking nonetheless. However, there are examples of internet architectural changes protocols that start here and then they spread, such as WebRTC, as discussed earlier. And Quick is an interesting example because it started as a Google project where Google had the incentive and ability to make a change in protocol stacks and applications as Gquick, the original version. But then standardization and coordination with other stakeholders was what was necessary for it to have global outcomes, but that also required global change control. And so it naturally progressed from one quadrant to the other in this sort of design space. Finally, there are two other quadrants, one that's rare and one that we think is better to avoid. Global outcomes with local change control is sometimes ideal, right? The ability to make a change but have widespread impact is quite rare. Sometimes government policy or a very large company can achieve this, but generally this quadrant we think is rare. And then another quadrant, local outcomes with global change control. This seems to be better to avoid because it's a difficult thing to do to have global change only to have a local outcome. So what we might do is we might then sort of take the next step in our thinking beyond this and think about how do we shift the architectural layer or change incentives to accomplish what we're trying to accomplish. So suppose you want to make an architectural change and you have a specific outcome in mind. We'd like to suggest that maybe there's a general principle here, which is shift the architectural layer to change the incentives of existing stakeholders, or even which stakeholders are in play for a given change or a desired outcome. So let's consider the two-axis diagram of change control versus outcomes. Shifting the architectural layer may move to a different quadrant, not always, but it sometimes may. And that new quadrant may be easier to navigate because of the incentive and/or stakeholder alignment in that quadrant. So an example of this, a mechanism that we're familiar with, overlays, our classic example, or underlays as sort of an argument extending that. Mechanisms to accomplish this, but they aren't the only such mechanisms. A shift in architectural layer may also involve a change in the protocol or the architectural approach entirely. If the outcome is what you care about, then the protocol can change, the architectural approach can change as you move to a different layer so that you change the incentives and change the stakeholders in play. And an example of that might be that you might have a different implementation if you have a global change control requiring L3 protocol and you move to the same or similar outcome and have local change control requiring L4 protocols. So it makes it easier because you don't require global change control. You operate at a different architectural layer. So the suggestion here in this sort of general principle might be to look for changing one or more of the following: the architectural layer, the incentives of the existing stakeholders, the stakeholders themselves that are in play, and the technical mechanism used to achieve the desired networking goal.
Following on from that, once you have the stakeholders, you want to have a stake in this architecture and the architecture that you're trying to build. Protecting this set requires end-to-end encryption. Now, this is not a new observation. The Tussles paper by David Clark and others from 2002 states it quite bluntly, and it remains one of the cornerstones of deploying new architectures today. Actually, deploying the architecture can be done by overlaying, as Bharat pointed out, or underlaying, but you should design the protocols in such a way that allow the architecture to get ossified underneath in the ways that you want and protect the rest above the encrypted layer. The encrypted layer becomes the layer that protects change control in the hands of the stakeholders above the layer from having to engage with those below the layer. This is an evolutionary principle that's worth restating. If you want to future-proof the stakeholders in your architecture, encryption is a strong way to enforce protection of these stakeholders from encroachment from accidental ones, specifically from the ones below. So tying it all together, the internet today is built by economic interests that have stakes in this architecture. This is an outcome of massive success, and we should celebrate that. If you want to build new architectures, then think about the architectural layer that you want to build it at. Think about the incentives of the stakeholders in there and the stakeholders that you want in there. And then use encryption to protect the architecture and its stakeholders from encroachment. This talk, just to be clear, is not meant as a recipe for success, but as an encouragement on how to make real architectural change based on our collective experience. We believe this makes the problem more interesting, not less, and it increases the chances of success. Thank you.